Hello, everyone, and welcome to an April section meeting of the ISA. I don't know. Oh. Hello? I'm sorry. Yeah. Oh, we're on. We're live. I'm Eric Keller. I'm the Vice President of the ISA section. I'm not quite as verbose as Dean is, but so this introduction will be relatively short today. Today's presentation is compressor surge modeling control by Greg McMillan. He's heading his way up here. A couple of quick items before he starts. First, thanks again to all our sponsors. Enough said about that, I guess. And then coming up, one of the big items Dean had wanted me to mention about is next month, May the 7th, we've got our section meeting. I think it's Michelli Calibration Labs. It's in, was it Harahan?
Brook Hollow Esplanade.
Brook Hollow Esplanade. It's going to be a tour of their facility. I presume that means there's no online next month.
There'll be lunch served and a calibration lab for.
Sure, but it'll be just
yeah, no
it'll be there's no web connection for that.
No web connection.
So everybody be aware, if you want to come and see that, there won't be any remoting in. And then at the end of May, we do have the exhibition and symposium at the Hilton Garden Inn Convention Center. That's preliminary to the District 7 Leadership Conference that'll be taking place that following week, that same weekend. And then Dean had mentioned it in the last meeting, but the Leo Hosenthal is preparing a control system engineering PE review course for some point in the future. Dean will, I guess, TBD, it'll at least be June before.
Summertime or for sure.
I guess, but as far as him supplying information to folks, there won't be any opportunity in May to do that.
No.
So it'll just be online distribution?
Keep post, yeah, there'll be emails about it for sure.
Okay. And then our website for upcoming events. And then here's the information on the tour with the location. The presentations are always available on the ISA website in case anyone's interested and in this tour next month and needs the address. It'll be on the website. And that's the end of my portion of the presentation. I will be passing it on. Let me set up the application and we'll go ahead with it.
Okay, great. Glad I got an opportunity here to discuss this. Gosh, this dates way back to my early days at Monsanto. I'd have to say some of the most exciting unit operations control systems I dealt with literally were compressors. I mean, these are compressors with at the Monsanto Pensacola plant. The rotors cost at that time, back in the 70s, maybe $10 million. And when the compressor went into surge, it could damage if you didn't get out of surge right away within a few cycles, you could damage it noticeably. And we only could afford to stock a few of these rotors. So if you went through a few of them, while you were shut down while you were replacing the rotor, but the whole plant would be shut down until they manufactured new rotors. There was a plant in Mississippi that had the same compressors. They said, we can't deal with this, but Monsanto said, hey, we're going to make these special rotors. We're going to keep running. And it was a very efficient compressor, just very challenging. It was an axial compressor, and it turns out axial compressors tend to get more damaged, and they're much larger by definition. And that's why you went to an axial compressor probably. And this particular one would go into overspeed in a fraction of a second, and we had to have a derivative unit module at that point. And back then things were like analog computing modules. So we computed the derivative of the speed as a backup to shut the whole thing down to help avoid damage. But also we put in surge control systems to prevent it from getting to that point so we could keep running. And I went from there to several other compressors, and they were all very challenging, very exciting. If you've ever been out in the field and you hear one of these compressors going in the surge, the big booming noise every 2 seconds is, and everything shaking is pretty dramatic. And every time you go into a surge cycle, there's some damage. It could be very slight to bearings and seals, but as you count up the number of cycles and you get into maybe 10 or 20 cycles, you have a noticeable loss of efficiency. So it's a very destructive, unsafe, and challenging application, because when you go into surge, even if it's not that crazy axial compressor, typically the flow will precipitously drop in less than 0.05 seconds, go negative. Now, you probably can't measure the negative flow, so it's not quite as exciting. But the fact that it's doing that, as you can imagine, how disruptive that can be. So this is me. I retired as a senior fellow from Solutia Monsanto. Monsanto spun off the chemical business into Solutia. Of course, Monsanto was bought by Bayer. Solutia was bought by Eastman Chemical. And also prior to that, Solutia sold the Pensacola plant to Ascend Performance Materials. So none of the companies I worked for exist by name. I don't know if that's been my goal in life or not. I was an adjunct professor at the Washington University for a while there after I retired, and currently I'm a software engineer at Emerson as a result of Emerson buying Minor Technologies. My specialty, even when I was at Solutia and Monsanto, because we were in I was in E&I engineering, and for like 7 or 8 years in the beginning. Started up and designed a lot of plants, and then went in engineering technology. In engineering technology, I was very fortunate. We had people that were the leaders in terms of modeling, whether it was steady state or dynamic. And in fact, Monsanto at that time wrote the Flowtrans software that they donated it to Aspen Research because they didn't want to commercialize it. And then at Aspen Research, some people decided, oh, we could start a company. And I took the Flowtrans software and became Aspen Tech. And I've looked at some of the code most recently because we were trying to check something out, and it is the original Fortran code, Flowtran. Anyway, I worked with those people like Harold Nell, Henry Chin, Bill Bowles, all these brilliant people, PhDs. I never got my PhD, so even though they would call me Dr. McMillan, I would say, no, I'm Nurse McMillan. But I learned an awful lot from them, and part of that was using dynamic simulation to learn. And I have all of Shinsky's books, and they were excellent. I just gave a tribute session, part of a tribute session for Greg Shinsky. How many people know who Greg Shinsky is? Raise your hand. Okay. Well, he was he was the key guy. Of course, his last book was in the 1990s, but most of his books were written in the 70s and 80s, and except Foxborough. And his books were unique still to this day because they go into, really what is the key principles you need to understand in the process, and what's the challenges then associated with that, what's the dynamics, also what are the automation system dynamics, and how are they going to affect things, and then getting into what can PID control do and all the options and capability in PID control. There isn't anything that approaches that. Unfortunately, all those books are out of print. And it's a commentary. Publishers don't understand what they took out of print, and it's unfortunate that I guess a lot of people at this point don't benefit from Shinsky. I've got all of his books. You can get his last 4th edition of Process Control, which really is a pretty good summary of a lot of what he developed. And you can go to Schneider Electric Education Department, and maybe they'll sell you that with some DOS software for a simulation he developed. Now, you're going to pay a couple $100 for it, but of course, you can't say I don't want it. They're going to package it. Interesting story there. And I don't take it personally either. Then that about half of my books are out of print. I put some of them back into print, most notably through Momentum Press. But anyway, I've written quite a few ISA books, and most recent Advances in Reactor Measurement Control, Good Tuning Pocket Guide. And I've been a monthly Control Talk columnist for Control Magazine since 2002, and a founder and co-leader with Hunter Vegas ISA Mentor Program. And so I would encourage anybody who's a practitioner, actually doing process control. It could be instrumentation, it could be electrical, it could be more IT focused, could be process control strategies, whatever. It could be configuration. We don't get into details of a particular system. We try to avoid that. We try to remain vendor neutral. My history is really as a user. It's only in the last 2 years I've become a part-time employee for Emerson. So my history as a user, and of course, Hunter Vegas, he grew up in Bay St. Louis, and he went to Tulane. He gave a talk here, so you may remember Hunter Vegas. He's an excellent co-leader of the mentor program. So if you're interested, just contact us. You can be either a resource or you can be a protege. And it's kind of, the lines are blurred because we have some proteges now with 10 or more years of experience. But we're just all, we talk and we have a monthly question and answers that develop into posts on the ISA automation site. It's a little confusing to find, but here it is, automation.isa.org. And they put it all under my name there, but they're Q&A posts for, the last 10 years for the mentor program. There were times when we were very busy where there was a lull. Now we tend to do a monthly Q&A post. Okay, if you know me, you probably know I have my top 10 lists and cartoons as part of Control Talk. And I have written some humorous books that the whole thing was trying to be technical, but also humorous. Kind of an interesting situation. Sometimes people don't quite what? Engineering can be humorous, but anyway. So top 10 things you want to hear from your CEO. And this is actually a little bit serious. It's sustainable, improvable plant profitability by the best automation system is more important than project schedules or costs. Seek online plant performance metrics with smart time horizons. Think they could understand what's smart? Take the time to learn new technologies and exploit, like the digital twin. Read and understand my books. Apply the best practices of the handbook we just finished, Hunter and I just finished. I've read and understood the automation competency model. I did a control talk column on this, and I don't think hardly anybody in ISA knew about it. And if you go to their website, you can find something about it, but it's really not a key part of it. It's some separate organization, the Automation Federation. But we actually have helped them revise this or update it in the last 10 years. And there's actually an automation competency model. And it goes into what we think are the skills that are beneficial for different types of jobs in the automation industry. No on-off valves posing as throttling valves. I want valves that don't compromise control. That's been my mission. Because it started out with surge valves causing all kinds of headaches, but it went way, way beyond that. People buying valves that were, because, you know, and they put on their spec sheet, what is the leakage? Oh, less leakage is better. So that was their primary consideration. Tight show-off valves. Piping valves that met the piping spec, had huge capacities, you know, big capacity, minimum leakage. What can be better than that, right? I want what is truly important for measurements in valves. That would be nice for a CEO to say that. And these are the links that are, when you see that, the hyperlinks. No low bid packaged equipment. Boy, I've been burnt by packaged equipment. Make innovative process control improvements. I'm not sure they would know what a process control improvement is. And finally, you decide what is best. Wouldn't you like to hear that? Okay, topics covered: compressor surge curve and set point, getting at the heart of the problem and really why we have this really extreme behavior. And we see that in terms of the curve, characteristic curve, and the path of surge, and flow and pressure oscillation, stern surge. And what can we do for compressor surge protection, efficiency maximization? What are the sources of the automation system dynamics? You know, compressor control systems are very sensitive to everything being fast enough. And the question is, how fast is fast? And how critical is that? How to make valve response faster? There's been big misconceptions that date back probably 50 years. Valve alerts are what you should be concerned about. Digital twin use, improvements, offered opportunities, and new blocks. And digital twin is the new name for doing a virtual plant. I've been told not to use that term anymore. And it has to do with the fact that the virtual plant may be considered to be something that necessarily is in the cloud. Even though it wasn't in our case, it was on our laptops. But anyway, the term is digital twin now, and we'll get into that. And I'm kind of understanding now why we say that, and how I've had to get with what really is the terms that marketing and people higher up than me really want to hear. Details on control system implementation. Best practices, and what are the resources? Okay, well, whoops. How do we advance? I wanted to go to the next page. I hit the arrow and it just rebuilds. So, space bar? Oh. Okay, the animation is kind of messing things up. So if I went through the whole animation again, would have moved to the next slide? I don't know. All right, we'll find out. Now, the objective is to keep the operating point to the right of the surge curve. So why not generate a set point that's kind of parallel to the surge curve? And it literally is a curve. And for a centrifugal compressor, it tends to have this type of shape, an exponential shape. Here, if it's an axial compressor, it would tend to bend over here. But for centrifugal compressors, it tends to just continue on like that. Each characteristic curve for a particular speed here gets steep, and then it gets flatter and flatter. And the point where the slope is 0 is the surge point. That's how you know you're at surge. Now, if you think about this, if you go along here, as the pressure goes up, you're going to have more of a driving force to force flow. So it'll tend to self-regulate itself to an extent, and it's got a negative slope here. That's providing the negative feedback in the process that is providing some self-regulation. So that helps. However, when you get to 0 slope, it's probably too late. Now you're very vulnerable. Now compressor manufacturers typically show this here. They don't show you what happens over here once you get to the left of the 0 slope. And that's where it gets really exciting and insightful. And that's what I do actually in the model. There, I found some key articles that had actually the momentum balance that will allow you to actually simulate the behavior as it deals with the curve to the left here. And the reason this is very hard to plot this curve to the left, and so, and I guess people wouldn't know really what they're looking at. Now here it shows as a function of speed, but it could be a function of vane position if you're using vane position to change flow. And so you would like it to be offset with enough of an offset so that you never get to the point of 0 slope. In other words, if you cross this set point here, it's going to open the surge valves and bring you back here. And of course, control is not perfect, so it's going to be overshooting in terms of where you want to be at. And so it will venture over in here. So you have to have enough of a bias here. How big that bias is depends upon how fast your instrumentation is and how intelligent your surge control system is. In general, by operating closer to the surge curve, you're lining up with the efficiency ellipses better. Also, you're preventing unnecessary openings of the surge valve. And of course, if you're opening the surge valve, you're wasting energy. So you only want to have to open up the surge valve if like you're really worried about an impending surge, getting too close. So this bias here, the idea is to minimize that. And one of the things you do is by using intelligence and understanding to make sure that you do that correctly. So we're going to look at what's on the other side of that surge curve. I know you're probably pretty excited about this right now, the mystery. Okay, and this was actually in the article, and what we'll look at the curve is plot number 2, and I apologize, it's not labeled there clearly, but this is plot number 2. So, you know, what you see is what's here to the right of the 0 slope. What you don't see is what's here, and this is negative flow. And the original research article was for like a compressor in a laboratory situation. So these flows are not very large. But anyway, the principles and the curves, this is giving you the insight to really what's happening. So you're at this point, and then you get to this positive slope of the characteristic curve. It creates positive feedback. Positive feedback in a process is very difficult. That's why exothermic reactors, highly exothermic reactors, can run away from you. It's due to positive feedback. So when you have that, it's a very difficult situation. And in fact, what it causes is the flow to jump from B to C to the point of there being significant negative slope, negative feedback. And it does that in 0.05 seconds. Incredible. Now, your flow measurement probably can't measure negative flow, so you don't know really how bad it is, but you can hear it and you'll see the consequences of it in terms of vibration and axial displacement and speed changes. Then what does it do? Well, it's got this negative slope. It says, well, I can walk along this. So it walks along this, and then it gets again to a point of zero slope and then positive slope. It can't follow this part here. It jumps to point A. And then if you haven't got the surge valves open far enough, it walks along to point B, jumps to point C, walks along to point D on the negative slope. The positive slope, then it causes a big jump way over here to point A, to the negative slope again. So these are the oscillations, pretty dramatic. It's interesting, these periods here are faster because it was like a laboratory or pilot plant situation. Industrial plants, the oscillation periods tend to be about 1 to 2 seconds, which are still incredibly fast. I once thought, well, if I just had a very fast analog control system and a very fast valve, it could get me out of surge. But these oscillations are so extreme, being a period of 1 to 2 seconds, you can just imagine what a feedback controller is thinking and trying to do in that time period. In fact, the clue was, I kind of knew this, but the operator, he saw these few surge cycles and he stepped in right away and put it in manual and opened up the valve to a point where it would prevent surge. And that turns out that is the solution. But you want intelligence to do that automatically, not rely upon an operator being that attentive. We were testing something, so we were very attentive, but that's not normally the case. And so I call it an open loop backup, and there's other ways of maybe accomplishing this, but you're not on feedback control. You're not on automatic control. You have taken some intelligence and you have positioned the surge valve to a point where it ensures you're to the right of the surge curve. And you hold it there for things to stabilize for maybe at least 10 seconds. And there can be additional intelligence, like you could start to slowly close it or even start to open it even more if you felt like you were too close to the surge curve. You eventually then let the feedback controller take over when everything is stabilized. Now, there's a lot of companies that offer proprietary, very sophisticated control strategies, and they may be more intelligent than that. But basically, they're trying to do the same thing, detect, hopefully, the approach to the 0-point slope, but more likely what they're doing is they detect a very rapid drop in flow. There's nothing else that's going to cause this flow to make that extreme drop in 0.05 seconds. I mean, if you can't measure in negative, it's going to go to whatever it can measure in 0.05 seconds. And that's the signal that they need to do something and do it proactively and not to go back to feedback control for a while. This is the control system we use typically. You have the standard PID feedback control system that is getting it's a flow controller on a suction flow. It's advantageous for it to be a suction flow measurement because you have less of an issue of pressure and temperature compensation. If you have a discharge flow measurement, you normally have to pressure and temperature compensate it back to the suction conditions. So it's advantageous to have a suction flow meter and then to have the pressure rise across the compressor that is like the y-axis of that compressor map to generate a surge curve, that surge set point that is parallel to the surge curve, and that becomes the set point for the flow controller. And then you would like to probably have more than one valve to protect you in case one of these stick, particularly if you're one of those people that said, okay, the best valve is the one with the highest capacity and lowest leakage. Well, it's often likely to stick in the closed position. And particularly if it's higher temperatures can cause it to stick and just not being used a lot. And hopefully that valve is not being used a lot, it's staying closed. And so it's more likely to stick. So you would like to have at least two valves. And then you need an open loop backup. And you need to make sure you're detecting the surge as a derivative of the flow to trigger that. And that then puts the controller, in this case, into remote output and holds it there with an intelligent output to prevent surge. Now, you may be wasting energy at this point, but for 10 seconds, it's the better thing to do than to damage your compressor and potentially shut down the unit. Then you can have your flow controllers. They can be sending a feed forward signal, and we have done this in cases in Monsanto, so that if we have one of these compressors feeding like 6 reactors, and so if one of the reactors shut down, we sent a feed forward signal to proactively open the surge valve to compensate for that. Now, one of the challenges is making sure that if the valve characteristic is not linear, how do you calculate that valve position that you need that matches the loss of flow from one of these users. But you can do it through understanding installed flow characteristic. I guess the good news is the installed flow characteristic is the inherent flow characteristic because the pressure drop across the control valve is so high. So you know what that characteristic is, and so you can make the proper feed forward calculation. Then the thing that you can do if you're interested in refining this to make it more efficient, you can put in a valve position controller that seeks to push the furthest reactor open valve to its maximum throttle position. You would never want to push it to 90 or 95% because often this characteristic gets kind of strange, often flattens up there. So you push it to a good point on the installed flow characteristic of the user valve where it has a good slope and it's going to be able to do its job of tight reactor flow control. So you choose the largest valve and say, hey, there is a maximum feed valve position that's still good for control. And then you say, I am going to lower the compressor pressure to force that more efficient operation. And this strategy was developed by Shinsky for a lot of different unit operations. You could do it to maximize cooling tower temperature or refrigeration unit temperature to save on energy there as well. There's a lot of different ways you can use valve position control. You can maximize feed to a reactor based on, say, some temperature control valve and the reactor being forced, say, on coolant to go to its maximum good throttle position. So there's a lot of that capability with valve position control. Now here I just show that, hey, these surge valves are not venting. They are going to recycle. And if it's going to recycle, typically there's a heat exchanger. It's because if it's going around in a circle, it's going to keep heating up. And so you have to make sure you're taking that energy out of there and cooling it so that it doesn't, high heat cause even more damage to the compressor. So it's basically a similar control strategy otherwise. Now I show here recycle, and this could be then what's used for compressors in series or multi-stage compressors. One of the companies that originally, I think, was a source of a lot of the knowledge on compressor control was called Compressor Control Corporation. I don't know if you've heard of them, but they came over, the guy came over here from Russia and he started that company, and Staroselsky, and wrote a bunch of key articles, very intelligent articles back, I think, in the 70s. And of course, he wants to sell you their special controller to do all of that. But you know, the articles were saying that, hey, whether it's compressors in series or stages in series, he advocated that there be separate surge controllers on each one of those stages. And that if you need to do some decoupling or feed forward, you can take care of the interaction that might occur between having separate surge control valves for each stage. And also, you may want to do some intelligent ratio of how much compressor pressure rise you have across each compressor, called compressor ratio dividing, pressure dividing. If you have compressors in parallel, they each would have their own surge control system, and you would be dividing up the flow requirements upon the compressors in parallel. But basically, each compressor, each stage would have a complete control system like this to protect itself. Now, this loop, people don't realize I think how many loops are really seriously affected by the automation system dynamics. And so this is, you know, this is your job, and you have the power here, and you should have the knowledge to make sure that you have the dynamics, the speed of response needed. And it turns out, if you look back in general, for pressure flow, in general, the dynamics of the control system, the automation system, are slower than the process. And so what you do there is going to affect the performance, how fast your system is. Now, with surge control, because you're trying to deal with a phenomenon that was extremely fast, you're taking this to the extreme. And so you want to make sure that you have the fastest valve, minimum delay, lag, and stroking time. Actually, we can approximate the valve response once you get beyond the deadband or resolution, which is a whole nother story, as a velocity limited exponential response. And so it's, you know, it's a slewing rate, but there's a time constant and pre-stroke dead time associated with that. And Compressor Controls Corporation, I think, I forgot what they said, maybe 2 seconds, but I think they're talking about big strokes. Anyway, it's more like 1 second is what you ought to make sure you have. So that's pretty darn fast, particularly if you're having like a 24-inch valve, right? Making sure it can get to the next position in less than 1 second. Then, you know, in the process itself, the time constants and dead times are a fraction, less than a second, could be milliseconds. And so then you get into, well, how fast is your transmitter? And what is the damping setting there? It turns out that if you were to put in a damping setting of 1 second, it would be way too slow. In fact, some manufacturers of transmitters, that was their default. And this one guy said, I'll never buy those transmitters again, because you know, he would change it from its default of 1 or 1.2 seconds down to 0.2 or whatever the lowest was. But somebody in the middle of the night would grab a transmitter, put it in with a default setting, and it would inevitably shut them down in the middle of the night because it was too slow. So it's something you have to be very attentive to. And then even the scan time. And Compressor Controls Corporation, one of the things they're saying is that you have to buy their controller because the scan time is like 0.05 seconds. Now, there's some DCSs and PLCs that can do that. And so you can do that there. It turns out from with studies we've done that, and you can kind of understand this, if your valve is going to take 0.2 or 0.3 seconds to start to respond, and maybe the rest of the second to respond, does it really matter so much whether this is 0.05 or 0.1 seconds? Anyway, But if you have any question or doubt, now one of the problems though, if this scan time says 0.05 seconds, you got to make sure that the filter associated with that very fast time scan controller is also small, because we've ran into some cases where you order these special controllers with very fast scan times, and what do they have? It doesn't make any sense. Why do you want a very fast controller if they're going to put in a 0.5 second time constant? It doesn't make any sense. But somebody who doesn't understand process control, he said, well, let's make it real smooth or something. I don't know. So you have to make sure that you know how to adjust those scan time filters as well to make sure that they're fast enough. And then the controller, of course, needs to be tuned for it. Okay, now one of the things that was really strange to me, a very brilliant person who will remain nameless, but he did Nyquist plot studies back in the 70s or 60s, I guess. And he concluded that if you have a fast loop, you should not use a positioner. How many people have heard that rule? Well, maybe it's a good rule from a standpoint of Nyquist plots, but when you get into reality, particularly with fast controllers, and more importantly, the situation I ran into, and that I did this because that's what I saw the paper, and it was not only a paper, it was like a prevalent guideline. And even my cohort, Stan Wiener, who I did the column with until his passing, and did co-author books. He still cited that rule: fast loop, use a booster instead of a positioner. Well, so I tried this out on a plant, and the technician said, "Oh, you better not do that, Greg." I said, "No, whoops. I've learned unequivocally I shouldn't have that positioner there, so I'll replace it with a booster." And that's what I did. That night, the compressor, when I started to run it, the surge valve slammed shut and the compressor shut down. Luckily, there wasn't much damage or any noticeable damage. And so we went out to that valve, and with the booster on here, excuse me, pressing the wrong thing. Just the booster on here, no positioner. Even though it's like a 24-inch valve, he could take his hand and move it up and down. So this was a butterfly valve. A little bit of turbulence or unequal forces on that disc could cause the shaft to move. And in fact, if you look, and it's not well acknowledged, but this booster has a high outlet port sensitivity and a kind of a low input port sensitivity. And I think is happening, because this is a diaphragm actuator. If you had a piston actuator, you'd have to have a positioner, right? But if you have a diaphragm actuator, this is what the rule was. What happens is, as the diaphragm flexes, it causes a positive feedback situation that then causes the booster to further go in the wrong direction. And that's why, even sitting in the shop there, you could walk up to it and move it, even though it's a 24-inch valve, just by grabbing the shaft. And so to continue the story, I learned right away, put the positioner back on, and you then have to open this bypass valve. Because if the positioner is seeing this very small volume now, it's used to seeing this big volume, it gets confused and gets very fast oscillations. Very fast, like maybe 1 hertz. And very noticeable if you're standing there, but if you're not standing there, of course, you don't know. So you have to open that bypass enough so that it sees this bigger volume. Of course, if you open it all the way, you've lost some of the speed. So you open it just enough to make sure that it doesn't oscillate. A few years later on furnace pressure control, and furnace pressure control is almost as challenging. In fact, this particular furnace, it could go off scale in a quarter second. Well, that was another furnace. In this case, it was 1 or 2 seconds. It could go off scale and trip the pressure. It's a very challenging situation. And so I ordered, I said I wanted fast valves, and they were big valves. And I told them the stroking time requirement. And I go to check them out at the factory, and I see they just have boosters on. So I walked up to them and said, hey, look what I can do with these valves. And I just moved the shaft of these valves wherever I wanted to. And they said, what? And I said, well, you need a positioner. And of course, this company was also where the person had first done the Nyquist plots, and we had brochures, on the wallway saying what you should do in terms of fast valve. But they said they found a paper back in the 1950s that said, you better do it this way. The booster on the outlet of the positioner with a bypass valve open. So they found that paper, and I was really thankful they did, because now I have a lot of support. But it's amazing how much today I still hear that. And it's a very potentially dangerous situation. Now, if it was, I don't know all the situations where some people are getting by with this without it being dangerous. I don't know. But the thing is, you need that feedback, correction, and protection supplied by the positioner. Long story. That's it. The other thing that's happening these days is when we had pneumatic positioners, it was high gain proportional only controllers, right? Gain was 50, maybe 100, 150. Then we got in these really fancy digital controllers, and now they're 3-mode controllers. Well, okay, PID, that's better than proportional only, right? Well, proportional only, if you have a gain of 50 or 100, it's tight control. So what happens though, if you have put in integral action, you have to back off on the controller gain. But even more importantly is that if you have any stiction and any backlash, you are going to create a limit cycle once the valve's trying to open and do its thing. And the rule is this: if you have one or more integrators in your system, whether it's in the positioner or the controller or in the process, you are going to get a limit cycle from stiction. If you have 2 or more, you're going to get it also from backlash and deadband. So here your flow controller has integral action. You add it in the positioner. Now you're going to get a limit cycle from backlash and deadband. And you're going to make the limit cycles from stiction worse. So the idea, and I've gone back to the guy really at the factory who does the testing, and he's frustrated because somebody in marketing decided it looks better when you do a test if you have integral action, right? It kind of holds to the set point, instead of an offset from proportional. And so someone decided the default is to have integral action on, but it's just not one company. Other companies, they're really proud of how they tune it as a PID controller. Clueless. At least we're kind of, on the company I work with, we know the problem, and we tell our customers that situation. Not used to saying customer. I've only worked for Emerson directly for the last few years, but this thing evolved over the last 40 years. Shinsky wrote about this, and I've studied it quite a bit, and it really is a shame that it's not understood. Yeah, so we really don't want integral action in the positioner. So valve alerts, common mistakes. Minimizing leakage, because that's what the valve spec has. Maximizing capacity, because that's what the valve spec says. Minimizing cost, right? That's good. What this leads to is more like an on-off valve. Watchouts. Actuators size for loose packing at room temperature. To help prevent this, we say, whatever you come up with, your vendor came up with as an actuator size, ask him to give you 150% more of that in terms of thrust or torque. Because he's sizing it for some conditions, saving you money with a smaller actuator, and that's what he stock. I get very sensitive to backlash and deadband for pH control, and there was some very good valves that had good specs, but then when we actually ordered them and said we want the deadband and stiction to be less than 0.25%, so we can't do it because the actuator we put on there, it's in the warehouse. That's the standard actuator. It's going to be 0.6 or something, 0.7%. And I said, well, let's replace the actuator. Well, it's a special then. It's not in stock. It'll take 3 months delivery. I didn't have 3 months anyway. So it's really frustrating. And Hunter Vegas and I are on the same page for a lot of things. And this is the same thing. He's frustrated too. Undersized actuators. A resolution and deadband tests are typically done positions greater than 40%. You ask the supplier, what is the deadband resolution? He inevitably is going to test it for greater than 40% because if he tests it near the closed position, where you're trying to minimize leakage and it's rubbing against the seal or rubbing against the seat, what happens? And it's amazing how much worse it gets, even if you're at 10 or 20%, how much worse it is. So if you're going to be operating at 10 or 20%, you ask them what is the resolution of deadband there. Response time tests, another mistake is they're done for greater than 1% or less than 10%. If they're done for less than 10%, you really don't see the effect of the slewing rate. If they're done for greater than 1%, you don't get into the actuator sensitivity, positioner sensitivity. It turned out some positioners won't respond at all to changes less than 1%. They're spool type positioners. And there's some very good positioners that unfortunately they don't respond if the change is less than 0.5% and they start to deteriorate and the response time goes from 1 or 2 seconds to like 5, 6 seconds. And then you get down to 0.25% and it goes to 40 seconds. And if you change directions, it goes to 80 seconds. Now, how small are those changes that your controller output is making? Are they 1%, 2% each scan? They often are making very small changes. And what happens? The valve doesn't move, or even worse, you get into oscillations. So on-off valves, pulsing and throttle valves, huge error between actuator shaft feedback and the internal ball disposition. There is a connection between the shaft to the stem, and then also from the stem to the ball or disc. If that stem to the ball or disc is not integrally cast, you got a problem there as well. And if the connection from the shaft to the stem is not a splined for a rotary valve, you got a problem there. It's amazing. Or when you talk about problem, it's like an 8% difference. And smart positioners give dumb diagnostics because they're looking at the shaft position. They think everything's okay. In fact, Stan Wiener was in the room with a smart digital positioner. He says, Craig, hey, we got a great valve here. And the plant had insisted on using their plant valves designed for tight shutoff and for pressure control. And I said, okay, well, let me just check out in the shop. Is that what it looks like the valve disc is actually a big butterfly disc is doing? They were making changes, and the smart positioner was saying, hey, we're responding to 0.5%. Hey, things are going well. The shaft is. You go out in the shop, the disc is not. So we put on a little travel gauge on the disc, and it turns out it would take 8% changes before the disc would actually move. Amazing. And then I saw another case where it was a ball valve, it was in a phosphorus slurry. They said, this is the only type of valve that will work. We have all these on-off valves for phosphorus slurry service. And so you got to use it. And so I said, well, yeah, but you have these wild oscillations. Oh, it must be some disturbance coming in from somewhere. The disturbance is caused by the valve. The key is if you put it in manual, the oscillations go away. Anyway, I took it in the shop, the same situation. Smart positioner saying everything's fine. Looking at the ball, didn't move for 8 or 9%. Booster using setup position, we talked about that, and then interval action, the positioner. Okay, I think if I do this one more time, it'll go. Yeah, okay. Interesting. So, I've used simulation to become much more intelligent all my life about these things, trying out these scenarios and being able to then, in a very safe exploratory environment, figure out really what's going on. And so here with the digital twin now, we have the actual control system, including configuration displays, alarms, and storing tools. And you can import, export, you can copy and paste. It is literally the same files. Now the I/O assignments, since they're not to the field, they could be. You could actually connect up to the I/O, but if you're doing it in terms of being not connected to I/O and you're connecting to the simulation, then of course the I/O assignment changes to be a simulation value instead of an actual field value. But anyway, you want to make sure, though, in the dynamic simulation, this is something not typically done, but it's been my focus, is include not only the dynamics of the process, but also the valves and measurements. And the control, well, the controller comes in through here, those dynamics there. But for the measurements and valves, you want to make sure you put them into the simulation. And then I think the key thing is here, you can show the before and after benefits of solution from online metrics. I was at the AICHE symposium and it was amazing. I mean, I kind of saw this and knew this, but the guys were saying, the operators are just putting things in manual and they don't, and you tell them, well, don't do that. But how do you prove to them that it's hurting the process by them putting it into manual if they're still running? It's a continuous process. And the only way really to prove that is to have some online metrics. And there are some plants that do that. And interesting enough, one of the more, established technologies, and maybe not all that complicated, I guess it's a little complicated, but ethanol plants. There's an ethanol plant manufacturer who has ethanol plants that are literally pretty much all alike. And he has online metrics showing what the plant A, B, and C, and D is around the country is doing, plus your plant, in terms of efficiency and capacity. And the operators tend maybe not to like it at first, but then they get competitive. And they say, well, we're as good as plant A, and it's literally the same system. So it really comes down to the operator. What is he doing? That's different. But it also helps with the process control engineer in terms of them knowing what their impact is, and also the recognition of the profession, which is something we really have to be concerned about, because that was the other thing that came out of the conference, how we go to some plants now and there's maybe only one person left. And how many people really get to look at process control innovation anymore? So we think that this could be the key. So opportunities, cause and effect, relationships, interaction, resonance, process, safety, stewardship, startup transitions, abnormal operations, something called procedure automation, automate how you handle with those situations, process response. We get to learn about all these things by using a digital twin. I've developed these blocks for compressor surge using momentum balance and including that characteristic curve you don't see that's mysterious, but the cause of all the crazy behavior. And future value that will detect and predict surge. It does with a good signal to noise ratio. And it looks at changes in the compressor characteristic curves. It can identify the slope. So if it sees a point of approaching zero slope, it knows you're very close to the surge curve, and you can capture that point and say that's surge curves can change with time and wear and tear with compressors, so it can update the surge curve. And then in order to make sure you understand the effects of deadband and stiction and the valve response, this is a key block right here. Some details, I think we've gone over this. So, well, I didn't say this, but that future value block really just keys on a dead time block. 'Cause that sounds bad, dead time block, but you're taking the input and the output and you're choosing a delay signal that gives you a good difference. And as soon as you get an update on the input, you have an update of the rate of change. So it's not like some calculations where you're like, oh, I wait a time interval and then make a calculation what the change was. Here, I get as fast as that scan rate is, like 0.05 seconds, I am getting an updated slope and an updated rate of change every 0.05 seconds. It's a kind of a misunderstood and well, I don't call it misunderstood, but a not recognized opportunity. And that plays a big role in the system. And it must open the surge valves for at least 10 seconds with a bumpless transfer back to feedback and surge control once the flow is stabilized. And the surge valves must reach 80% of the opening demanded in less than 1 second. For pressure control, the requirements are almost as fast to help prevent surge and high pressure shutdowns. And the surge must go wide open, valves must go wide open on air, electrical, or signal failure. Compressor suppliers should provide the surge curve for different operating conditions. The surge curve should be updated online by the detection of approach to the flat part of the characteristic curve. Precipitous drop in flow, negative flow may not be measurable by the flow meter and may be prevented in some cases by equipment and piping design, including check valves. The number of surge oscillations and the amplitude oscillation should be historized along with the number of excursions to a flat characteristic curve that did not result in surge, but indicated you were really darn close. This requires a fast historian update time. The point at which the surge valve starts to open can be determined by when the contribution from the proportional mode exceeds that of the integral mode. If the integral contribution does not drop below the proportional contribution until reversal of sign, the surge valve will not open until the suction flow drops below its set point. In general, that's getting a little dangerous, and we want the integral contribution not to overrule the proportional, and it should, it's going to start out at the output limit. And so you can, there are some features that allow you to take care of that to make sure that that doesn't happen where the integral mode overrules the proportional mode until it's too late. Best practices, accurate surge curve for different operating conditions provided by the supplier for each compressor and stage, particularly for changes in suction composition. Surge curve should be updated online by detection of operating flow and approaching a flat part of the characteristic curve, indicating approach to curve and a precipitous drop in flow in less than 0.05 seconds, indicating an actual surge. Number of close approaches to the surge curve and the number of actual surge cycles along with the surge amplitude should be historized. The historian must not have compressor. And here I said 0.2 seconds. The previous slide said 0.1. Prefer 0.1. Surge control valves must fail open. And I think I said that before. Resolution deadband should be less than 0.4% near the closed position. Last set here, transmitters must have damping set to minimum. Controller execution rate must not be slower than 0.1 seconds. Some people would say 0.05 seconds. Signal filters greater than 0.05 seconds must not be used. An open loop backup must activate and hold the surge valves open. Talked about that before. Initial surge lines and control valve must be to prevent each compressor or stage from going into surge. For compressors in series or stages, the total pressurizers requires ratio into individual pressure control set points for the compressors or stages. For compressors in parallel, the total flow requires ratio to individual flow set points for the compressors. This is the resources. I just finished with Hunter Vegas, the 6th edition of this right here, which has a section on surge control, more importantly about nearly every process control system you're going to run into. But if you want to get into the specifics of surge here, this is a Control magazine article. You want to get more details on the digital twin and virtual plant, there's this article. Then on the consequences of common mistakes and things you don't realize are going to be a problem. This one, how you want to make sure you specify valves and positions that don't compromise control. And then there's this book that I put back in print by Momentum Press, Centrifugal and Axial Compressor Control. ISA originally published it, but they let it go out of print. And then, of course, the handbook. Sorry I ran over, but there was a lot I tend to talk about. Yeah.
Any questions in the room? We'll hand the mic so the web audience can. Quick question. My formative years, the players were CCC, then CAC, and then Petrotech.
Okay.
And I've been kind of out of that area for a while, but how common is this now to have products and services related to surface control? Is there hundreds of vendors or a dozen? What's the scope of that?
Well, I was surprised. I only knew of Compressor Controls Corporation, but I've seen maybe about 3. And it turns out now that Emerson has put logic in there that would say you don't have to go to a special person to get this. And that was one of the challenges. Not only you have to go to a special supplier, but it's, there's special hardware. If you have a problem, what do? You have to maybe rely more upon them to understand and fix it and make sure it's running right. So we're trying to, I always put it in the Provox or Delta V. And it worked quite well, but you need to have some intelligence when you do it. And these standalone controller companies, they kind of use scare tactics, personally. And it's a pretty scary situation, so they can get by with that.
Thanks. All right, any questions online, feel free to chat in real quick. I'll give you a second to do that if you want to ask. Anything else in the room? Looks like it's all quiet there, Greg, so if you want to, okay. We'll wrap it up.
All right, that's it. I encourage you to, let's take process control forward. Let's not just do copy jobs. Let's do innovation. And I think the key to that is, being able to demonstrate and work with your management. To me, spending some time investigating and learning these things is worthwhile. It's been my life. Okay.
Very good. All right, Greg, appreciate that and everyone attending. And we'll make these links available to everyone. And if Greg is nice enough to let us share the presentation, we'll do that as well. So we'll post all that online. So we'll wrap it up. Thanks again.